There is a moment in every act of discovery when a machine built by human hands turns its eye towards something that was never meant for us to see. Not a planet, not a star, not anything born in this solar system, orbiting this sun, shaped by the same swirling disk of dust that made the Earth beneath your feet. Something older, something from somewhere else entirely. And on a quiet day in August of 2025, that is exactly what the James Webb Space Telescope did. It focused, it opened its infrared eye, and it looked directly at a visitor from another part of the galaxy. Its name is almost deliberately unglamorous. 3I/Atlas. The 3I tells you everything about how rare this moment is. This is only the third interstellar object ever confirmed to pass through our solar system. Not the third comet, not the third asteroid. The third object of any kind that we can say, with confidence, came from outside the gravitational reach of our sun. Before it, there was Oumuamua in 2017, the strange, cigar-shaped wanderer that some scientists still argue about to this day. Then Borisov in 2019, a comet that behaved more or less like a comet should. And now, in the summer of 2025, a third traveler arrived. Except this one didn't just pass by quietly. This one gave us the chance to really look. Let's set the scene because the scene matters. On the 1st of July 2025, a robotic survey system in Chile called ATLAS, the Asteroid Terrestrial Impact Last Alert System, a network of telescopes built specifically to catch things that might hit us, noticed a faint point of light moving in a way that didn't belong. Most objects in the solar system move in closed loops, ellipses, obedient paths that keep them tethered to the sun forever. This object was not obedient. This path was hyperbolic, open-ended, a trajectory that comes in once and leaves forever, never to return. Astronomers ran the numbers, and the eccentricity of its orbit came out to just over 6. For comparison, a perfectly circular orbit has an eccentricity of 0. An orbit like Halley's Comet, elongated and dramatic, comes in around 0.97. This object blew past even the most extreme comets we know. It wasn't just visiting. It was passing through on a one-way ticket stamped by some other star system entirely, sometime, somewhere, long before humans existed to notice. And here's a detail that should stop you for a second. Astronomers now estimate this object could be somewhere between 3 and 11 billion years old. Let that number sit. Our solar system is about 4.5 billion years old. There's a real chance that the ice inside this comet, the ice that Webb was about to analyze, formed before the sun that warms your skin right now had even ignited. This is not an object from our neighborhood. This may be an object older than our neighborhood itself. To understand why this moment mattered so much to the scientific community, you have to go back to the first time humanity ever caught one of these wanderers red-handed. In October of 2017, a telescope in Hawaii spotted a strange, elongated object tumbling through the inner solar system, moving too fast to be bound by the sun's gravity. It was given the name Oumuamua, a Hawaiian word roughly meaning a messenger from afar arriving first. It was gone before most of the world's best telescopes could properly turn toward it. A red, oddly shaped, tumbling object that seemed to accelerate slightly as it left, in a way that didn't perfectly match the behavior of an ordinary comet venting gas. That small, unexplained acceleration set off years of debate, speculation, and more than a few outlandish headlines, some of them suggesting, only half-jokingly, that humanity had just missed its first encounter with an artificial object. The truth, most likely, is far less dramatic and far more interesting. Oumuamua was probably a fragment of hydrogen ice, or a wisp of a shattered planetesimal, behaving in ways too subtle for our instruments to fully capture in the brief days we had to watch it. But the frustration of that missed opportunity lit a fire under an entire generation of astronomers. Never again, they said, would an interstellar visitor slip through our fingers without a fight. 2 years later, in 2019, a second visitor arrived, Borisov, discovered by an amateur astronomer in Crimea, and this time, at least, it behaved like a proper comet, complete with a visible tail and a fairly ordinary chemical composition, offering something like closure after the mystery of Oumuamua. But 2 data points do not make a pattern. Scientists were left with a tantalizing question. Are these 2 visitors typical of what drifts between the stars? Or were we simply lucky enough, twice, to catch objects that happened to be relatively easy to explain? The only way to know was to wait for a third. That wait ended on the 1st of July, 2025. And this time, humanity was ready in a way it had never been before. Survey telescopes were sharper, follow-up networks were faster, and in orbit, nearly 1 million miles from Earth, sat the most powerful infrared observatory ever constructed. A telescope that didn't even exist when Oumuamua tumbled past us, unstudied and unexplained. By the time NASA's Hubble Space Telescope caught its own portrait of the object on the 21st of July 2025, the world's astronomers were already scrambling to redirect every instrument they could toward this fleeting visitor. Because here is the brutal truth about interstellar objects. You don't get a second chance. Oumuamua came and went before most of our best instruments could even lock onto it properly. This time, astronomers were determined not to let that happen again. And that is where the James Webb Space Telescope enters the story, not as a supporting character, but as the instrument that would, over the following months, completely rewrite what we thought we knew about this thing. On the 6th of August 2025, Webb pointed its near-infrared spectrograph NIR-SPEC, for those who like their acronyms, directly at 3I/Atlas. Understand what this instrument actually does. It doesn't just take a picture. It splits light apart the way a prism splits sunlight into a rainbow, except far more precisely, revealing the exact chemical fingerprints hidden inside that light. Every molecule absorbs and emits light at very specific wavelengths, like a barcode written in physics. Webb reads those barcodes from millions of miles away, and what it read was startling. The coma, the hazy cloud of gas and dust that surrounds an active comet's nucleus as it warms and begins to vent material into space, was dominated by carbon dioxide. Not water, which is what powers most of the comets we know from our own solar system, but carbon dioxide in overwhelming abundance. Alongside it, Webb detected water ice, water vapor, carbon monoxide, and a curious sulfur-bearing molecule called carbonyl sulfide. This was a chemical signature unlike almost anything cataloged in our own cometary neighborhood. Imagine spending your whole life studying apples, and then someone hands you a fruit that is almost an apple, same rough shape, same basic biology, but with a completely unfamiliar chemistry inside. That is roughly the position planetary scientists found themselves in. Then the object continued on its path. It swept in toward the sun, reaching its closest approach, its perihelion, on the 29th of October 2025, at a distance of about 1.5 times the distance from the Earth to the Sun. Even at its closest, it never came anywhere near threatening our planet, staying comfortably beyond 100 million miles away throughout its entire passage. But that close encounter with solar heat did something important. It woke the comet up. Sunlight baked its ancient, billion-year-old ices, releasing them into space with new intensity, giving scientists an even richer plume of material to study as the object began its long journey back out into the dark. For a while, though, nobody could look. The comet swung behind the glare of the sun from Earth's point of view, vanishing into that blinding light for weeks, invisible to every telescope on the ground and most in orbit. And then, in December of 2025, it re-emerged, battered by solar heat, brighter, more active, and utterly transformed. This is when the story took its strangest turn yet. Webb turned its attention back to 3I/Atlas, this time deploying a different instrument. MIRI, the mid-infrared instrument, capable of detecting wavelengths of light invisible to the human eye and largely invisible even to Webb's other instruments. Observations were carried out on the 15th and 16th of December, and again on the 27th, as the object drifted outward at a distance of roughly 2 astronomical units from the Sun, more than 200 million miles. And in that data, astronomers found something that had never, in the entire history of astronomy, been directly detected in an interstellar object before: methane. Sit with that for a moment. Methane, the same molecule that seeps from Earth's swamps, the same molecule that fills the atmospheres of Jupiter and Saturn's moons, the same molecule some scientists watch closely on other worlds as a potential, if ambiguous, signature of biological activity, detected, for the first time ever, drifting off the surface of an object that formed around a star none of us will ever see, in a part of the galaxy none of us will ever visit. This wasn't just an incremental data point. This was a genuine first. And the methane told a deeper story, too, once scientists dug into how much of it there was. The comet's methane production rose sharply as it moved away from the sun, a pattern that suggested something quietly poetic. As the comet's surface layers were stripped away by the heat of its solar encounter, the methane closest to that surface, the shallow methane that had likely been slowly cooked off over billions of years of quiet interstellar wandering, had already been depleted long before it ever reached our sun. What Webb was now detecting was fresh methane, welling up from deeper, more pristine material, untouched, unprocessed material that had been locked away since the object's formation, sealed beneath the surface like a diary nobody had opened in billions of years. In other words, the closer scientists looked, the more they realized they weren't studying the comet's outer shell anymore. They were reading pages that had never been exposed to starlight until this very year. But methane wasn't alone. Webb's mid-infrared spectra also picked up the unmistakable fingerprint of atomic nickel, glowing in a specific, forbidden electron transition at a very precise wavelength, nickel vapor, essentially sublimating directly from solid material into gas without ever passing through a liquid phase, a process scientists sometimes jokingly compare to dry ice, except this is metal behaving that way in the vacuum of space, heated by sunlight from 93 million miles away. This detection of metallic vapor in a comet's coma is itself a rare and relatively newly understood phenomenon, one only recently confirmed in a handful of solar system comets. Finding it here, in an object with no connection whatsoever to our own solar system's formation, hinted that whatever cooked this chemistry into existence, wherever and whenever that happened, followed remarkably similar physical rules to the ones we know. And then there was the isotope story, arguably the most profound piece of the entire investigation. Webb's instruments were sensitive enough to measure the ratio of deuterium to hydrogen in the comet's water, deuterium being what scientists call heavy hydrogen, an isotope with an extra neutron riding along in its nucleus. This ratio acts almost like a thermometer frozen in time, a record of the temperature and conditions under which the ice originally formed billions of years ago in some distant, long-vanished protoplanetary disk. And the ratio Webb measured did not match anything typical of comets born in our own solar system. It pointed toward an environment that was colder or chemically distinct, or simply built under different rules than the disk of gas and dust that eventually became the Earth, Mars, Jupiter, and everything else we call home. Astronomers, working backward from these numbers the way a detective reconstructs a crime scene from a handful of fibers and a fingerprint, began to sketch out a story. 3I/Atlas most likely formed around a star that existed long before our own sun ignited, in a region of the galaxy chemically different from our solar neighborhood, and then spent an almost unfathomable stretch of time, potentially billions of years, drifting silently through interstellar space, tumbling through the black, between the stars before gravity and chance finally sent it drifting past our sun. Every molecule Webb detected in that coma is, in a very real sense, a message written before human civilization, before human beings, before most of the animal kingdom as we know it, arguably before the Earth itself had fully cooled from its own formation. There's something almost dizzying about that thought, and it's worth pausing on it rather than rushing past. When you look up at the night sky, you are looking at light that, in many cases, left its source so long ago that the star itself may no longer exist. When Webb studied 3I/Atlas, it wasn't looking at ancient light, it was looking at ancient matter, physical material, atoms and molecules that had been drifting through the galaxy since before Earth had oceans. This comet isn't a message from the past in the way starlight is. It is the past, physically here, in our solar system, letting us touch through the language of spectroscopy, a chemistry born under a sun that may have died before ours was even born. As the observations accumulated, other telescopes joined the effort, filling in pieces Webb alone couldn't capture. Radio observatories detected methanol and hydrogen cyanide woven into the object's chemical inventory. NASA's SPHEREx mission, a wide-field infrared observatory built to survey enormous swaths of sky, tracked a striking increase in carbon monoxide production after the comet's closest approach to the sun, along with a new emission signature suggesting the presence of organic material carbon-based molecules, the same broad category of chemistry that, on Earth, eventually built proteins and then cells, and then everything alive around you right now. To be clear, and worth being precise about, because sensational claims about alien signals tend to swirl around every interstellar visitor. This is not evidence of life. It is evidence of the raw chemical ingredients that, under the right conditions, over unimaginable stretches of time, can eventually lead toward life. It's the difference between finding flour, sugar, and eggs on a countertop and finding a finished cake. But even finding the ingredients out here drifting between the stars is a profound thing to witness. Meanwhile, astronomers tracking the object's color noticed something else worth mentioning. After its solar flyby, 3I/Atlas began appearing progressively bluer. In the world of comets, color shifts like this often signal changes in the size or composition of dust grains being shed from the surface, or shifts in which gases are dominating the outgassing process at any given moment. It was, in effect, one more sign that this object was not a static, frozen relic simply reflecting sunlight passively. It was alive in the purely physical sense, actively evolving, actively venting material, actively transforming before our instruments in real time, the way a living thing responds to a changing environment, even though nothing about it is biological. There was also an asymmetry noticed in its water production. More water vapor detected after its closest solar approach than scientists would have predicted based on models built from studying solar system comets. Every one of these small, seemingly technical observations adds another brushstroke to a portrait of an object that keeps refusing to behave the way our local intuition says a comet should behave. And that, more than any single dramatic headline, is the real story here. It's not that 3I/Atlas did one shocking thing. It's that, observation after observation, instrument after instrument, month after month, it kept quietly declining to conform. It's worth taking a moment to appreciate the sheer engineering miracle that made any of this possible in the first place. The James Webb Space Telescope sits nearly 1 million miles from Earth, at a gravitational balance point called the second Lagrange point, far beyond the orbit of the Moon, tucked behind a sunshield roughly the size of a tennis court, folded up like origami during launch and unfurled, piece by piece, once safely in space. That sunshield's job is simple to describe and staggering to achieve. Keep the telescope's delicate instruments colder than -200 degrees Celsius, cold enough that the telescope's own heat doesn't drown out the faint infrared whispers of the universe it's trying to hear. Its mirror, built from 18 hexagonal gold-coated segments, unfolded in space and aligned to a precision smaller than the width of a human hair, gathers roughly 6 times more light-collecting area than Hubble ever could. All of that, the folding, the unfurling, the cooling, the alignment, had to work perfectly on the first try with no possibility of a repair mission, 1 million miles from the nearest human being. And it did. It worked. And because it worked, when a fragment of another solar system came tumbling past our sun for the first and only time, we had, waiting in the dark, an instrument sensitive enough to actually read its story. There's also a broader statistical question lurking behind all of this that tends to get overlooked in the excitement of any single discovery. How many objects like this are actually out there? Based on the discovery rate of just 3 confirmed interstellar visitors in under a decade of dedicated searching, and accounting for how difficult these objects are to detect, small, faint, moving fast, visible only for a narrow window before they're lost in sunlight or distance, some researchers estimate that at any given moment, there could be thousands of interstellar objects passing through the solar system that we simply never notice, too small, too dim, too far from any telescope. Currently scanning that particular patch of sky, 3I/Atlas is not a freak occurrence. It is, statistically speaking, simply the latest example of something that has almost certainly been happening for the entire multi-billion-year history of the solar system. Stray fragments of other star systems drifting through our neighborhood, unnoticed, unphotographed, unread, long before humanity ever built an eye sharp enough to catch one in the act. Even the observation process itself carried a strange kind of drama, the sort of thing that rarely makes headlines but says something about how fragile and precise the science really is. During the December MIRI observations, 2 of the planned exposures failed because Webb's guide star tracking system briefly lost lock. A purely technical hiccup, the kind of thing that happens occasionally on the most sophisticated machine ever placed in space. Astronomers simply rescheduled and captured the missing data days later, with slightly shorter exposure times. It's a small reminder that even a telescope orbiting nearly 1 million miles from Earth, engineered with mirrors coated in gold and instruments cooled to nearly absolute zero, still has to fight for every single photon of ancient starlight it manages to capture from something as faint and fleeting as an interstellar wanderer. None of this happened in isolation, either. Behind every spectrum, every chemical ratio, every carefully worded line in a research paper, sits a sprawling international effort. Astronomers in the United States, in Europe, in Chile, in Japan, coordinating telescope time across observatories that rarely, if ever, get pointed at the same target within the same narrow window. Proposals for Webb's observing time are normally submitted years in advance, competed for by thousands of scientists chasing a limited number of hours on the most oversubscribed telescope in history. But interstellar objects don't wait for the normal process. When 3I/Atlas was confirmed, astronomers had to invoke Webb's director's discretionary time, an emergency reserve set aside precisely for moments like this, for the rare, unrepeatable, time-critical events that the universe doesn't schedule around human bureaucracy. Teams that might otherwise be scientific competitors, jostling for the same limited resources, found themselves collaborating, sharing data, cross-checking each other's results, because everyone understood the same unspoken truth. There would be no second sitting for this portrait. Whatever they managed to capture in these few months was, quite literally, all humanity would ever get. And if you sit with the data for a while, the way the scientists analyzing it clearly did, something else becomes hard to ignore. Every spectral line Webb captured, every trace of methane, every whisper of nickel vapor, every subtle shift in the ratio of heavy hydrogen to ordinary hydrogen, is a piece of physical evidence that the universe builds its raw materials the same way, over and over again, in wildly different corners of the galaxy, under wildly different stars, separated by unimaginable distances and unimaginable stretches of time. The molecules found drifting off 3I/Atlas are not exotic, alien compounds requiring some entirely new branch of chemistry to explain. They are water, carbon dioxide, methane, carbon monoxide, the same molecules found in comets born right here in our own solar system, the same molecules found in the atmospheres of gas giants, the same molecules, ultimately, that make up a meaningful fraction of your own body. The universe, it turns out, is not infinitely inventive. It tends to reach for the same basic ingredients again and again, wherever gas and dust and gravity are given enough time to work. That is either a deeply comforting thought or a deeply unsettling one, depending on how you choose to look at it. Comforting because it suggests a kind of underlying unity stretching across the entire galaxy. Unsettling because it means that whatever else might be out there, built from those same ordinary ingredients, might not be nearly as different from us as we sometimes like to imagine. So where does that leave us, now, with 3I/Atlas continuing to recede, continuing to fall away from the sun on that same hyperbolic path that will carry it out of our solar system forever, never to return, never to be studied again by any telescope humanity builds this century, or the next, or possibly ever? It leaves us with an object that arrived carrying billions of years of chemical history sealed inside its ice, an object that revealed, for the first time in the history of astronomy, direct evidence of methane venting from something born around another star, an object whose very deuterium ratios whisper about environments and epochs we can only reconstruct through inference and careful measurement, never through direct experience. There's a reason scientists chase objects like this with such urgency, spending nights redirecting billion-dollar telescopes toward a fast-moving point of light that will be gone within the year. It's the same reason a historian might drop everything to examine a single page torn from a book otherwise lost to time. 3I/Atlas is not just a comet. It is a fragment of a story we will otherwise never get to read, the story of another star system, another disk of dust and gas, another corner of this galaxy, that quietly assembled its own version of comets and planets and ice long before Earth existed, and then, through nothing but blind cosmic chance, sent one small piece of that story drifting across 90 trillion miles of empty space until it happened to cross paths with us. And maybe that's the real reason this story is worth telling at all. Not because of any single dramatic discovery, not because of methane or nickel vapor or ancient ice, but because of what all of it means when you step back and look at the whole picture. We live on a small, rocky world, orbiting an unremarkable star, in an unremarkable arm of a fairly ordinary spiral galaxy. And yet, in the span of less than a decade, we have built instruments sensitive enough to intercept messages from other star systems entirely. Not radio signals, not deliberate transmissions, but honest, physical, chemical messages, embedded in ice and dust, carried across unimaginable distances and unimaginable time, and we have learned to read them. 3I/Atlas will leave us soon. It is already leaving, right now, as you listen to this, falling back out into the dark between the stars, carrying its billion-year-old secrets away from the only telescopes in the universe currently capable of reading them. It will likely drift for billions more years after this brief, fleeting encounter with our small corner of the galaxy, and it is entirely possible that no intelligent species will ever study it again, that this handful of months, this one narrow window in the 14 billion year history of the universe, was the only chance anyone, anywhere, will ever get to ask this ancient traveler where it came from and get something resembling an answer. That is, in the end, what a moment like this teaches you about the nature of discovery itself. It is not permanent. It is not guaranteed. It arrives briefly through a combination of chance, timing, and the patient work of scientists who spent years building instruments precisely so that, when a moment like this appeared, humanity would be ready. We happened to be watching at exactly the right moment in cosmic history, with exactly the right tools to catch a piece of another star system as it passed silently through our own. And for a brief, fleeting window, an object older than our sun let us read its chemistry, and in doing so, let us glimpse, however faintly, the vast, unseen architecture of a galaxy filled with countless other systems, other disks of dust, other slow, patient chemistries quietly assembling their own version of what we call a solar system, most of which we will never see, and almost none of which will ever send us a visitor as generous, as strange, or as quietly profound as this one.